Okay, SL kids, it's time for discussion 8.1, Introduction to Acids and Bases. Alright, so properties of acids. Let's do physical first. Physical properties. Acids will produce hydrogen ions in water. And you see here H3O plus is called the hydronium ion. Now, H plus and hydronium are interchangeable because the hydronium ion is just a hydrogen ion that attaches to a water molecule with a coordinate bond. So, acids will taste sour. They're good electrolytes because they produce ions when put in water. And really the definition of an electrolytic solution is one that has ions in the water. They will show a pH less than 7. Now let's talk about the chemical properties. This is a little bit tougher. When we talk about the chemical properties, we're going to talk about reactions of acids and what they react with. So we know that they'll react with bases in a neutralization reaction to form salt and water. They'll also react with certain metals to produce hydrogen gas, and we'll learn in Unit 9 why only certain metals will react with acid. They'll react with carbonates and bicarbonates to produce carbon dioxide gas, as well as a salt and water. Now, bicarbonates are compounds that contain the hydrogen carbonate or bicarbonate ion. This is just a carbonate ion that has a hydrogen attached to it, so its formula is HCO3-. And they'll react with ammonia to form an ammonium cation. So they turn blue litmus paper red, and kind of a simple way to remember that is blue to red, acid. Now, it's not really that great, but once you get the hang of it, you'll know that acids turn blue litmus red. Alright, so let's look at some of those reactions in equation form. So when they react with a metal, we said they'll form hydrogen gas. So we see the magnesium metal will form magnesium chloride with the chlorine, and then the hydrogen ions will produce hydrogen gas. They'll react with carbonate compounds. So here we have calcium carbonate with HCl. Again, it says they'll form water, carbon dioxide, and a salt. In this case, the salt would be calcium chloride, and we'd form water and carbon dioxide. And then we react with ammonium. It should say we'll form an ammonium salt. And we see here HCl reacting with ammonia will produce ammonium chloride. If it was sulfuric acid with ammonia, it would form ammonium sulfate, etc. Alright, so let's talk about bases. Physical properties of bases, they will produce hydroxide ions in water, generally. They have a bitter, chalky taste, like Tums. They're also electrolytes because they produce ions in solution. They will feel soapy and slippery and have a pH greater than 7. So the chemical properties of bases are fewer. They will turn red litmus paper to blue, which you can remember by saying basic blue. They'll also react with acids to form salts and water, just like acids will react with them. And they do not react with metals, and this will become important in topic 2. Alright, so the pH scale. We know that a neutral pH is 7. Anything that's greater than 7 is considered basic, up to 14. And anything between 7 and 0 is considered acidic. Now, the pH scale is connected, as we will find out, to the concentration of hydrogen or hydronium ions in a solution and the concentration of hydroxide ions and thus the pH. So if a solution is neutral, it will have a hydrogen ion concentration of 10 to the minus 7 and a hydroxide ion concentration of 10 to the minus 7, which will show a pH of 7. If the solution has a pH of 0, then it will have a hydrogen ion concentration of 1 mole per liter, a hydroxide ion concentration of 10 to the minus 14, and a pOH of 14. And we'll see how you can actually calculate these relationships later in the discussion. So these are just some common substances and what their general pH values are. So we see that ammonia, the household cleaner, is slightly basic with a pH around 12. Blood is very, very slightly basic with a pH just above 7. And milk is actually slightly acidic. And we see vinegar, lemon juice, and stomach acid are all there at the lower end of the pH range. Alright, so neutralizations. Again, an acid will neutralize a base, giving salt and water as products. So here are some examples. Now, we see when an acid reacts with a base, the salt that is formed will contain the cation from the base and the anion from the acid. So in the first example, we see the anion from the acid is chloride, and the cation from the base is sodium. So the salt form will be sodium chloride. With sulfuric acid and sodium hydroxide, it would be sodium sulfate. Phosphoric acid with potassium hydroxide would give potassium phosphate. And calcium hydroxide with hydrochloric would give calcium chloride. Now these are just double replacement reactions, so the cations essentially switch place and join up with the new anion. Alright, so environmental significance. This is an IB course, so this is stuff we have to know. Now normal rain will have a slightly acidic pH, and it's got a pH value of around 5.6 or more. Now this is caused from the carbon dioxide that is naturally in the atmosphere. When carbon dioxide reacts with water, it will form carbonic acid, which is a weak acid. So we expect normal rain to be a little bit acidic. Now, acid deposition is a process which will produce rain with a pH of less than 5.6. So the definition of acid rain is rain that has a pH lower than 5.6. You can't just say it's rain that's more acidic than typical. You have to actually know that value of less than 5.6. So acid deposition is caused by nitrogen and sulfur oxides that are produced, in vehicles, generally in industry as products of combustion. And so one example would be nitrogen dioxide, which will combine with water to form nitric acid, or sulfur trioxide, which combines with water to form sulfuric acid. Now, if you look in your note sheet, you will also see reactions for NO and SO2. Now, if nitrogen monoxide reacts with water, you'll form HNO2, or nitrous acid. And if sulfur dioxide reacts with water, you'll form H2SO3, which is known as sulfurous acid. So acid deposition, again, is just the process, whatever it may be, that produces acid rain. So combating acid deposition, we have to know about pre-combustion methods and post-combustion methods. So naturally, pre-combustion methods are those that are used on fuel before it's burned, and they really involve just the cleaning of coal, which is known as mineral benefaction. So what they do is they'll crush coal and use flotation, the different densities of the different compounds in coal, to reduce the sulfur and other impurities from it. And post-combustion methods are techniques that utilize complementary technologies to remove sulfur dioxide, nitrogen oxides, heavy metals, and dioxins before they're released into the atmosphere. So basically, they just scrub the exhaust or the products of combustion before they're released from the smokestack. So an example of that is the use of lime or calcium oxide. So one example, when calcium oxide reacts with sulfur dioxide, they'll form solid calcium sulfate. Because that solid calcium sulfite, because that calcium sulfite is formed, it's no longer going out of the smokestack as smoke, and it can actually be used in the production of sulfuric acid, so it's kind of a win-win. Alright, so definitions of acid and bases. When we think of an acid and a base, we'll usually think of hydrochloric acid and sodium hydroxide, because we use those all the time. And they will fit into both of our definitions of acid and base, but there are really broader definitions that we can use for acids and bases that don't necessarily contain H plus or OH minus. Now there's three major definitions, two of which you're responsible for. One is the Arrhenius model, the second is the Bronsted-Lowry model, and the third, which you are not required to know for SL, is the Lewis theory of acids and bases. So let's start with Arrhenius. An Arrhenius acid is any substance that, when put into water, will increase the concentration of hydrogen ions. And bases are substances in water that increase the concentration of hydroxide ions. Nothing really new to learn there. Now, a good thing about Arrhenius acids and bases, it's really easy to sort substances into acids and bases, because we'll see compounds that feature hydrogen ions or hydroxide ions. But the problem with it is that many bases actually don't contain hydroxide ions at all. Ammonia and the carbonate compounds are a great example of that. So now let's talk about Bronsted-Lowry. A Bronsted-Lowry acid is a neutral molecule, anion, or cation that donates a proton. Now it's important to note when we're talking about a proton here, what we're talking about is a hydrogen ion, because a hydrogen atom is one proton with one electron. Once it loses that one electron, the only thing that's left behind is a proton. So we'll use that term proton with the symbol H plus interchangeably. And a Bronsted-Lowry base is a neutral molecule, anion or cation, that will accept a proton. So the general form of a Bronsted-Lowry reaction would have the acid in blue, HA. Now, a Bronsted-Lowry acid is a proton donator, so in this process, HA has given up its proton to become A-. And B, and that little two dots represent a lone pair of electrons on B, B will then gain that hydrogen because it is acting as a base. So it goes from B to Hb+. Notice the charge of B increased by 1 because it gained a proton. And the charge on HA became -1 because it lost the proton. So an actual example of this would be hydrochloric acid reacting with water. HCl is acting as a Bronsted-Lowry acid, donating a proton to H2O, which acts as a base to become H3O-. Now we call these pairs conjugate acid and base pairs. All right, now this is an operational definition. Okay, so the classification in Bronsted-Lowry as an acid or a base will depend on how the substance behaves in a chemical reaction. And a Bronsted-Lowry base does not necessarily contain or produce hydroxide ions like we can see in the case of chloride. Okay, so what is a conjugate acid or base? A conjugate base is the species remaining after the acid has transferred its proton. And the conjugate acid is the species produced after the base has accepted a proton. So if we look at this example here, we see that the conjugate base to HCl is chloride, Cl-, right? So the conjugate base is what remains after HCl has lost its proton. And the conjugate acid to the base water is what remains after the base has gained its proton, so it becomes H3O+. All right, so conjugate acid-base pairs will only differ by one hydrogen ion. No more, no less. And you'll actually see a lot of questions asking about, like a multiple choice that says, which of these four pairs are a conjugate acid-base pair? And the answers to those questions are really obvious because the pair will only differ from each other by one hydrogen. So HA and A- are a conjugate acid-base pair. They only differ by a hydrogen. And we could say that A- is the conjugate base of acid HA. And B and Hb+ are a conjugate acid-base pair. And Hb+ will be the conjugate acid of base B. So here's some more Bronsted-Lowry systems. Now, these are all reactions involving water. And we see here that water can be either an acid or a base. So we see here water acting as a base. In each case, water is gaining a proton to become H3O+. And in these examples, we see water acting as an acid. Water can lose a proton to form hydroxide ions. And it makes sense that OH- or hydroxide would be the conjugate base to an acid. So water can act, as we said, both as an acid and a base. That means it is amphiprotic. The definition of amphiprotic is that a substance can act as a Bronsted-Lowry acid or a base because it has the ability to either donate a proton or accept a proton. Now we have a similar definition for a word called amphoteric. Now this is a more general term. That means a substance can act as an acid or a base. Not necessarily a Bronsted-Lowry acid or a base, but it could act as an Arrhenius acid or base, like the period 3 oxides of aluminum and silicon, like we talked about in Unit 2. All right, so amphiprotic refers specifically to Bronsted-Lowry, and amphoteric refers to just about everything. Okay, so hydronium. Hydronium, again, is H3O+, and is used interchangeably with H. So one example, we'll have HCl and water. If we show the dissociation of HCl, and we include water in our equation, then we have to write our products as H3O+ and Cl-. But if we wanted to just write H+, we could just avoid having water on the reactant side, making sure to use state symbols for the products of aqueous, which would tell us that water is present, even though we're not seeing it in the equation. And you'll see both examples of that. So here's a little practice. Take a moment and pause the video and list the conjugate base for those three species. Now, we know that the base will be what is left behind when those species have lost one hydrogen atom, or one hydrogen ion, I should say. So remember to mind the charge. And then take a moment and list the conjugate acid, or the species that remains after the base has gained a proton, for those three examples. Okay, so there are the answers. When HCl loses a proton, it becomes Cl-. When H3PO4 loses a proton, it becomes H2PO4-. And when H2CO3, carbonic acid, becomes, when it loses a proton, it becomes HCO3-. And that is our bicarbonate or hydrogen carbonate ion. And when sulfate gains a proton, it becomes HSO4-. And HSO4-, when it gains a proton, can become H2SO4. And when the nitrate ion, gains a proton, it becomes HNO3. Okay, so I just want to ask, which of these species are amphiprotic? Which ones could become an acid or a base? Now, I see here that H3PO4, if we look at the bonding around the phosphorus, phosphorus has as many bonds as it can handle, so it cannot take any more hydrogen. So it can only act as a Bronsted-Lowry acid. But H2PO4 could either gain a proton to become H3PO4 or lose one to become HPO4 2-. Same thing with HSO4. HSO4 could lose a proton to become sulfate, or it could gain a proton to become H2SO4. But sulfate is an example of something that is not amphiprotic because it doesn't have any hydrogen to lose. It can only act as a base and gain hydrogens. Okay, so the relationship between pH and concentration. Well, pH is defined as the negative log base 10 of hydrogen ions or the negative log base 10 of hydronium ions. Remember, those two things, hydrogen and hydronium, are interchangeable. This means that if we know the pH and we want to calculate the hydrogen ion concentration, we just take the inverse log, or raise 10 to the negative pH. Now, P is just an operator, and P stands for negative log. So P anything is just the negative log of anything. That means if we wanted to calculate POH, POH would just be the negative log of hydroxide ion concentrations. And if we wanted to know what the hydroxide ion concentration was, knowing the POH, we would just take 10 and raise it to the negative POH. So basically, if you know one of these things, then you know all of them, because we have our final relationship, pH plus POH equals 14. And later on in the discussion, we'll look at an example of that. So how can we use pH equation to figure out simple problems? Well, because of the logarithmic relationship, a 1 unit change in pH will correspond to a 10-fold difference in concentration. So an example says a solution of HCl has a pH of 2. How does that compare to the concentration of a solution with a pH of 4? Well, we know that the pH of 2 will have more hydrogen ions than a pH of 4. Since they're separated by, the pH values are separated by 2 units, that would be a 100-fold change. So the solution with a pH of 2 will have 100 times more hydrogen ions. So a more concentrated acid will have a lower pH, and a more concentrated base will have a higher pH. So take a moment and pause the video and practice these examples. Okay, so if a solution has a pH of 3, it will have 10 times more hydrogen than a solution with a pH of 4. The difference in pH is 1 unit, so 10 to the first, or 10. A solution with a pH of 2 has blank times more hydrogen ions than a solution with a pH of 5. Well, that is a difference of 3 units, or 10 to the third, or 1,000 times more than a solution with a pH of 5. And a solution with a pH of 3 will have 100 times less than a solution with a pH of 1. All right, so here's a little bit of practice using concentration to determine pH. It says for aqueous solutions 1 through 4, what is the correct order of increasing pH of these solutions? So take a moment and try to work this one out. Okay, so we know that the lowest pH will be the most concentrated acid. And the species with the highest pH will be the most concentrated base. So the order should go most concentrated acid, least concentrated base, most concentrated base. So we see that choice 1 is more concentrated than choice 2. So I know it's going to start with 1 and 2. So I can automatically rule out C and D. Now we know that 3 is more concentrated than 4. So the order should be 1, 2, 4, 3. So choice B is our answer. Here's another practice. Take a moment and work on this one all on your own. All right, so there's a difference of 4 pH units between 2 and 6. So the difference between them will be 10 to the 4th or 10,000. All right, now here's practice calculating pH, POH, H plus, and OH minus. So we have a solution of sodium hydroxide that is 0.010 molar. Now, we'll learn later that for a strong base, the concentration of hydroxide is equal to the concentration of the base. So our hydroxide ion concentration will be 0.010. Now we can go ahead and calculate the POH, because POH is the negative log of OH. So the negative log of 0.01 is 2. Now we have our relationship between POH and pH, and then we'll always add up to 14. So if our POH is 2, then the pH is 12. And if we know the pH and want to calculate the hydrogen ion concentration, we just take 10 and raise it to the minus pH. So the hydrogen ion concentration here will be 1 times 10 to the negative 12th molar. All right, so finally, titration. This is something we talked about in Unit 1, and it's something we're going to do as a lab in class. So titration is a technique that we're going to use to determine the concentration and thus the pH of an acid or base solution by using a known concentration and known volume of another acid and a base. And the formula we use is N sub A times the concentration of acid times the volume of acid equals N sub B times the concentration of base times the volume of base. Now, our factors here, lowercase n and sub A and n sub B, are the number of moles of hydrogen ions per acid or hydroxide ions per mole of base. So example, if we wanted to look at N sub A for HCl, every 1 mole of HCl will produce 1 mole of hydrogen and 1 mole of chlorine. So Na for HCl is 1. Sulfuric acid will produce 2 moles of hydrogen ions for every 1 mole of compound. So Na for it would be 2. And A and B in brackets are the concentration of acid or base, respectively, in moles per liter. And VA and VB are the volumes of acid or base in cubic decimeters. All right, so here's an example of a titration. The student titrated a sample of HCl with an unknown concentration. She found that 40 cubic centimeters of a 0.1 molar sodium hydroxide solution was required to reach the equivalence point. What is the concentration of the unknown HCl? So take a moment, use the titration formula, and work this one out on your own. Okay. So here's our titration formula. We are asked to find the concentration of acid. It's HCl, so Na is 1. The volume of acid is given to us. We know Nb for sodium hydroxide, its concentration, and its volume. So we're going to plug our values into our equation. Make sure to convert the cubic centimeters into cubic decimeters. Now, just so you know, when you're calculating concentration, it doesn't really matter because the volumes will cancel out anyways, the units of volume. But it's easier just to always convert to cubic decimeters. That way you don't have to figure out when. Because when you're calculating for volume, if you were, then you would need to convert them. All right, so when we solve for the concentration of HCl, we get 0.13 mole per cubic decimeter. And that is all for discussion 8-1. Feel free to bring any questions you have to class. Watch this video over and over again until you're prepared for this test. Thank you again for watching.